This video is about resonance. You should already be able to draw Lewis structures for all compounds and identify their polarity, but by the end of the video you should also be able to draw Lewis structures for compounds with resonant structures and determine which resonant structure is the most favorable using something called formal charges. And that's we're also going to determine bond order. It sounds like a lot, but they're actually not too bad. So the question of the video is there more than one way to obey the octet? So if you look at CO2, the top one is the way we've been drawing it since year one, where carbon bonds in double bonds to oxygen to show all of its electrons, right? So oxygen came with 6 electrons each, so 12, and another 4 for carbons for a total of 16 electrons. And we show that as 2, 4, 6, 8, 10, 12, 14, 16. And everybody has an octet, 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8. On the next picture, though, it actually does obey the octet. The oxygen still has 2, 4, 6, 8. The right oxygen has 2, 4, 6, 8 around it, and the carbon has 2, 4, 6, 8 around its bonds. And it still shows 16 electrons. 2 on the left, 4, 6, 8 on triple, 10 on the single, 12, 14, 16. 16 electrons. So, are any of these better than the other? Let's get into it. So first, let's try out NO3. Maybe pause the video, draw the nitrite ion as much as you can on your own. The way I might draw that is a couple of different ways. It doesn't work as single bonds. If you tried it with single bonds, you'll notice that you didn't have enough electrons to fill the octets. So you can decide if you want your double bond on the first oxygen, on the second oxygen, or the third oxygen, and it shouldn't matter, right? It shouldn't matter where I put the double bond as long as I have a double bond. If you try to put 2 double bonds, that also will not work because then you won't have accounted for all of your electrons, or something will be exceeding at this point. So in that case, we can show it 3 different ways. That is what we mean by resonance. So as notice that the nitrate ion can be drawn 3 different ways. It appears that there are 2 single bonds and 1 double bond. However, when measured, actually the bonds are all the same length. That is really interesting. So there isn't a short stubby double bond and 2 long single bonds. When we actually measure it, the bonds are all the same length. That means that there is no such real thing as single and double bonds. I'm blowing your minds right now, right? There is an area where the electrons might be shared, and they might be sharing it only 2 electrons, or they might be sharing 4 electrons, and that can be on any of these oxygens at any given time. So they're kind of migrating throughout the compound, and we don't know where they might be. So instead of saying there's 2 singles and 1 double, we're kind of saying that there's a double that rotates around. Let's talk about resonance a little bit more before we get confused. So resonance is when one or more balanced structures that obey the octet can be drawn for one molecule. They're called resonance. The electron placement changes, but not the nucleus. So you're not changing where the C's or the O's are. You're changing where your double bonds are. The arrows between the structures means they're all equal, not that the structure is changing. And resonance is used to fix the delocalized electron model, meaning that Lewis structures show electrons are definitely right here, but we know they aren't. Heisenberg says they're constantly moving. We're showing where they might be at any point in time. So in fact, the electrons are delocalized and moving, meaning that they're free to move around the molecule and not in fixed position. How do you show that on a 2D representation? You show it in a couple of different ways. So if we were to draw N2O4, maybe again, pause the video and see if you can draw at least one type of N2O4. Count up your electrons. Each nitrogen has 5 valence electrons, and oxygen has 6 electrons for a total of 34 electrons. You might start with a skeletal diagram where everything is connected. N's in the center because they're least common. And so far you've shown 2, 4, 6, 8, 10. Then you start putting electrons in to get your octets, and you end up being deficient in octets. And you keep working and putting in double bonds until you see something like this. It might work that the double bonds will be both at the top, catty-cornered, or any variation of this, maybe both on the bottom, catty-cornered in the opposite direction, both on the left, both on the right. In that case, we want to know which one might be better. It turns out there might not be any better option in this case. We're just showing that you can pick where you want to have your double bonds. So some molecules and ions exceed the octet, we saw that in the previous video, and they might not have equivalent resonance structures. One of them might be better than the other. They might have different numbers of double or single or triple bonds. So to determine the best structure, we might use formal charge. And if we use formal charge, the formula is here. You should write it down. It's the number of valence electrons from the atom depending on what group they're in. So like group 14 should have 4 valence, group 15 should have 5 valence, group 16 should have 6 valence, group 17 should have 7 valence, and group 18 should have 8 valence. And then we're subtracting the valence that are actually assigned to the structure. How many valence did you actually give it when you drew it? So how many it should have minus how many it actually has in the structure. Let's show some examples. So the rules are, lone pairs count as belonging to that, as one electron belonging to that atom once. And in shared pairs, so that each dot counts once, 1, 2, 3, 4. And in shared pairs, one electron belongs to the first element, and the other electron belongs to the second element. So in a single bond, for example, this left single bond between S and O, one of those electrons is oxygens, and one of the electrons is sulfurs. So it counts 1 for the atom. In a double bond, that means one of the electrons in the first bond is sulfurs, and the second bond is sulfur, so sulfur has 2 here, but oxygen also has the other 2. So if we were to try to figure out which of these sulfates is better, they both obey the octet, they both can exceed the octet, it's working fine. But let's try to figure out with formal charge which would be better. I might go in and put my formal charges in. So this sulfur should have 6. It has 1, 2, 3, 4, 5, 6 bonds, so it is a value of 0. These oxygens that are double bonded should have 6 valence. It has 1 on each bond, so 1, 2, 3, 4, 5, 6, so it's also 0, so is this one. On the outer oxygens that are single bonded, it has 1 per bond, and then 2, 3, 4, 5, 6, 7 dots. So it should have 6, but it has 7. 6 minus 7 is -1. Do you notice that these formal charges add up to the overall charge? So it's kind of like a little trick. The S is also 0, sorry. So it's a little trick that your formal charges add up to your overall charge. And what it's showing is the oxygen has a negatives. In this example, it's obeying the octet. I would actually just right away consider that better. But if you were doing it in terms of formal charge, just put them around. So remember the single bonded oxygens were negative, so I'm going to put all those in. And then the sulfur should have had 6, but 1 per bond. 1, 2, 3, 4. 6 minus 4 is 2. Does this add up to -2? I think so. So that's a good check on your work. Which one is better? The one that's better in terms of formal charge is the one that has the least number of formal charges. So in that case, in terms of formal charge, the double bonded structure is better. In fact, maybe I should make them all double bonded. Who knows? So I only chose this one because it was obeying the octet. So let's go through this. Structures that obey the octet are always the best structure. If you don't have one that obeys the octet, then the one with the lower formal charges is a better structure. So let's practice and pick the best resonance structure. If we draw XeO3, maybe pause the video and see if you can draw it yourself. Xenon would be in the middle with oxygens around the outside. It does work as single bonds, and this would probably be the best structure because it obeys the octet. But you might have drawn one with double bonds in any location, maybe on the bottom, the left, or the right. Maybe you drew a couple of double bonds, and so on. I'm just going to stick with these 3 for now. I love the first structure because it obeys the octet. But if you went through the rest of the structures, you would probably go through and see if they have their formal charges written out. Xenon should have 8 valence electrons. Right now it has 2 dots and then 4 bonds, which is 6. So 8 minus 6 is +2. That's already showing a pretty bad electron formal charge. Oxygens that are double bonded were 6 and 6, so zeros, and these were -2s, -1s each. Or here, xenon should have 8. It has 1, 2 dots, 3, 4, 5, 6, 7, 8 bonds. So it has 8, and all these oxygens have 8, right? 6 like it should. 1, 2 per bond, and then 3, 4, 5, 6 for dots. So this has actually no formal charge, and so I would say this is the second best structure. Let's do it for ozone. Oxygens in a row. You could probably draw it as the first structure where the double bonds on the left, or the second structure where the double bonds on the right. Do you think it matters in this case? I would argue it doesn't matter because not only is the number of bonds the same, single, single, double, double, they're literally mirror images of each other. So they're almost the same exact thing. Remember, it doesn't mean that they're moving structures, it means their electrons are moving. The electrons are moving from the first bond location to the second bond location. I would say that they're equal structures, and that's why we put an arrow between them. We didn't put an arrow between the top ones because they were not equal. I like this one better because it obeyed the octet. Last thing we need to talk about is bond order. It refers to how many bonds are shared. So if there's a single bond, we call it a bond order of 1. If it's a double bond, we call it a bond order of 2. And if it's a triple bond, it's a bond order of 3. The higher the bond order is, the stronger that bond is because they're sharing more electrons. Triple bonds are stronger than single and double bonds, which we saw 2 videos ago. Why are we talking about this? This sounds like the easiest thing ever. Let's look at some examples and you'll see why. What is a bond order of SO4 in this drawing? I see all single bonds, so I would say it has a bond order of 1. How about an oxygen, where I see double bonds? We would say it has a bond order of 2. Or a nitrogen, where it says triple bonds. Remember that the electrons between them constitute bonds. And then I would say triple bonds, bond order of 3. But in SO4 drawn in a different resonance structure, you have double bonds and single bonds. There are 2 double bonds and 2 single bonds. So these two have bond orders of 2, but the single bonds have bond orders of 1. What would you say the entire structure's bond order is then? I would say it's an average between the 2 1s and the 2 2s would be a bond order of 1.5. So you can actually have single bonds and double bonds and triple bonds, but if your structure has multiple different types, you're going to kind of average out where you think that bond order is. And why? Because remember, we can actually move these double bonds around. They don't need to be in the top and the right oxygen. They could be in the bottom and the left, or the top and the bottom, or the left and the right, whatever combination you like the best. But wherever they are, what the 1.5 is telling you is, remember what we said resonance really meant? It really meant that there is no such thing as a single, double, or triple bond. It means that they're sharing electrons, and those electrons are free to roam. And because they're free to roam, there isn't a really long single bond and a really short double bond, and an even shorter triple bond. There's a mush in between. A 1.5 means it's somewhere between all 4 of these bonds, are somewhere between a 1 length and a double bond length. They're at a 1.5 bond length. I don't know how we would show that. Maybe we'd show like a long line and a short line to represent that, but they've decided to show it as resonance structures, where some of them are double and some of them are single, and they rotate around, and that means that their bond order is 1.5, somewhere between single and double bonds. So back to the question of the video, is there more than one way to obey the octet? Yeah, these both obey the octet, but is one of them better than the other? They both have 8 valence electrons. They both have bond orders of 2, right? Whether it's double bonds or at an average of 3 and 1. And they both have a linear geometry. So it honestly doesn't matter which way you want to draw it so far until you get to formal charge. If you go through the formal charge, oxygen should have 6 valence. It has 1 on each bond and 1 on each dot, so 6. And then this oxygen is the same. The carbon should have 1 on each bond, so 4, and it should have 4 minus 4. This one actually has 0 formal charge. What about the bottom one? The oxygen should have 6, and it has 2 dots, and 1 per bond, 3, 4, 5. So 6 minus 5 is plus 1. Oxygen should have 4, it does, 4 bonds. And oxygen over here should have 6, but it has 1 on the bond, 2, 3, 4, 5, 6, 7. These, because they have formal charges, are not as nice, and that's the reason we've never drawn it that way, formal charge. So, you should be able to draw Lewis structures and try to draw a resonance structure of that, moving around your double bonds, and seeing which one's more favorable by either using the octet rule or formal charges. And also determine the bond order, which is another way of thinking of the strength and length of the bond.